Today I want to talk about superdosing. It's something that's been in the media an awful lot in the last 2 or 3 years, and various people have different ideas of what superdosing is. Where are the benefits coming from superdosing? And I want to define it specifically in my situation as being using enough phytase to prevent the buildup of IP3 and IP4 in the gut of the animal. That is not the typical definition that people use when they're talking about superdosing, but hopefully as I go through this presentation you'll understand why I'm using this as the definition of bringing about the benefits of superdosing. Phytases have traditionally been thought of as a means to provide phosphorus from IP6, and all phytases are called phytases because they attack IP6 and make from it IP5, which is a new substrate which phytases continue to attack. IP5 is then made into IP4, another phosphate removed and you generate IP3, and another phosphate is removed and you generate IP2. The final product of a phytase is IP1. No phytase breaks down IP1, but fortunately alkaline phosphatase in the gut is a very rapid enzyme and it will digest IP1, producing inositol and the final phosphate very rapidly indeed. So what we see there is the 6 phosphates have been removed, 5 of them by phytase and 1 by alkaline phosphatase. That is how people have traditionally thought of using phytases. Most people are looking at removing approximately 50% of the phosphorus from phytic acid. So we are still looking at a considerable amount of IP6, 5, 4 and 3 left in the gut of the animal undigested. What I want to do on the next few visuals is to show you why I think we've got to consider the IPs 5, 4, 3 as being significant anti-nutrients just as much as IP6, and to stop considering phytases as simply a means of delivering phosphorus. Now what do I mean by IP6, 5, 4, 3, 2 being a problem? If we consider from these sets of slides the rate of destruction of IP6, you can see a very rapid reduction in the concentration of IP6 when a phytase is used. In fact, within 40 minutes, all of the phosphate in this study was removed from IP6, producing IP5, which can be seen on this slide in the red line. IP5 is produced very rapidly from the breakdown of IP6, but you can see that it only reaches a small peak, at which point it then starts to drop in concentration. And that's because the enzyme even more rapidly attacks IP5 than it was attacking IP6. And that's a key point. Phytase does not have a similar appetite for IP6 as it does IP5, IP4, 3 and 2. And that I'm going to show you in the next 2 elements of this slide. You can see the IP4 and IP3 concentrations rise as IP5 is broken into IP4 and IP4 is broken down into IP3. But you can see the rate at which the enzyme is attacking IP4 and IP3 is quite slow, particularly for IP3. And that means that you see a build-up of IP4 and IP3 when we use a phytase in the animal. And that's actually just been shown recently in vivo experiments. And the final product is IP2, which you can see being produced in this set of visuals, is still being produced even after 3 hours of incubation. Now the interesting thing about this particular piece of work is that they were looking at the influence of phytate and phytase on the ability of pepsin to digest protein. So this visual that I've just shown you isn't just showing you the breakdown of IP6 to 5 to 4 to 3 to 2, but it's also about to show you the influence that this has on the ability of pepsin, which is in the same test tube as the phytic acid and the phytase, the ability of that pepsin to break down protein. And that's what this line is showing you here. So you can see at the very beginning of the experiment where IP6 or phytic acid concentration was quite high, it was very high, there's virtually no pepsin activity. Now, everybody recognizes IP6 as being a significant anti-nutrient, but the interesting point is all of the IP6 is destroyed by 40 minutes. And you can see pepsin activity is only at about 20% of maximum activity at this point in time. So clearly IP6 is not the only malevolent ester in this game. IP5 is clearly present at high concentrations at this point in time and it's being broken down rapidly. But even when the IP5 has disappeared at around 60 minutes, the activity of pepsin is still only 20% of maximum. You can see IP4 is completely removed at about 120 minutes and still the pepsin is only 70% active. And it's not in fact until IP3 has disappeared that you see full activity of the pepsin. So this is the first piece of in vitro work that tends to suggest that we should not just think of phytic acid or IP6 as being the only anti-nutrient when we talk about phytase and phytic acid. In fact, we've got to start thinking about IP5, IP4 and IP3. This visual shows another interesting facet of the differential properties of the esters IP6, IP5, IP4 and IP3. What we can see on the y-axis here is the solubility of zinc and how that's influenced by pH in the presence of IP6, 5, 4 and 3. And you can see at pH 3, zinc is wholly soluble, 100% soluble, regardless of whether there's IP6, 5, 4 or 3 present. As the pH rises towards pH 5, you can see that IP6 precipitates 100% of the zinc in the solution. And IP5 precipitates almost 85–90% of the zinc in the solution. And you can see at pH 6, IP4 is precipitating 100% of the zinc that was present, and IP3 is precipitating 65% of the zinc that was present in the solution. Now, why is this interesting? It's because the pH in the small intestine, as material moves out of the stomach, rapidly moves up from pH 3 to about pH 6 in a very short period of time. Right at the entrance into the small intestine, there is the pancreatic duct, which is secreting a lot of enzymes involved in protein digestion, trypsin, chymotrypsin and elastase. And all of these enzymes require zinc as a cofactor. And this zinc is actually secreted out of the pancreatic duct into the small intestine, where the pH is roughly 6. Now, if we have IP4 and IP3 coming out of the stomach, it's quite soluble at IP3, as you can see, but the minute it moves into the small intestine at pH 6 and the zinc appears out of the pancreatic duct, the consequences could be quite significant. And precipitation of the zinc would thereby reduce the activity of these proteases, making protein digestion less efficient. How do we know IP3 and IP4 are involved in degrading the ability of the animal to digest its feed? This recent data from 6 months ago shows that if you measure the concentration of IP4 and IP3 at the terminal ileum in birds that have been fed various levels of phytase, you can see that there's a very negative correlation between the concentration of these esters and digestibility of energy, dry matter, nitrogen, sodium, magnesium and iron. And if you look at the correlation coefficient, or the R values here, they're incredibly high and very significant, which suggests that IP4 and IP3 really are quite malevolent esters in the digestive tract. They are not innocuous. And we have ignored these esters in the past with all of our research. And today, what I want to identify is that destruction of IP4 and IP3 is of great importance if you want to superdose correctly. What evidence is out there in the literature that suggests that enzymes or phytases will increase IP3 and IP4 levels in the gut of the animal? This recent work by Pontoppidan et al. Is an interesting piece of work looking at the use of phytases in pigs. It's a phytase from Citrobacter brachii. And you can see on the left-hand panel, where no phytase is used, the ratio between IP6, IP5 and IP4 and IP3 is given above the bars in the feed, in the stomach. S1 is the first half of the small intestine and S2 is the second half of the small intestine 1 hour after feeding and then 2 hours after feeding. So you can see the ratio is about 1 to 0.2 to 0.1 to 0 in the feed. And this doesn't really change as you move down the intestinal tract. And in fact, as you increase in time. And that's to be expected because there's no phytase present, there'll be no breakdown of the IP6 to IP5, so you wouldn't get any change in the relative concentrations of these esters in the animal's intestinal tract. If we now look on the right-hand panel of this visual, you can see the effects of feeding 500 units of a Citrobacter brachii phytase. As you can see in the feed, of course, there is no difference compared to the control, as the phytase doesn't have an environment where it can work. But when we move into the stomach 1 hour after feeding, you can see from the visual a slight reduction in IP6 concentration, which is what you'd expect, but it's been broken down and it accumulates as IP4. And this is new. This is not something that was known or shown up before in previous pieces of work. If we then move on to 2 hours after feeding and look at the terminal ileum, as indicated in the visual by the red bar now, you can see a huge increase in IP4 concentration as a result of using the phytase. So compared to the control animals, the use of the phytase has reduced IP6, which is good, we know that's an anti-nutrient, but actually it's manufactured a considerable amount of IP4 which was not present in the control animal. We believe, and we've shown, this is an anti-nutrient, so in fact what we've done is we've degraded one anti-nutrient and simply produced another. That's the key, and that's why I mentioned at the very beginning, to my mind, superdosing is the use of sufficient phytase to prevent the buildup of IP4 and IP3. If we look at the use of another phytase with slightly different enzymatic characteristics, what we can see from this work in chickens is that if we compare control animals with those fed 500 or 1500 units of this particular product, Quantum Blue, you can see in this particular case there isn't actually a buildup of IP4 when we use the phytase. There's a very significant reduction of IP6, which is what you'd expect, and that's almost disappeared when you've used 1500 units as a superdosing dose. IP5 concentrations are reduced when we use 500 and 1500 units, but the IP4 is the interesting point. Notice the 500 units does not build up IP4 compared to the control, and superdosing actually reduces IP4 concentrations compared with the control. If we look at IP3 concentrations, what you can see here is that the lower dose of phytase actually results in a slight increase in IP3 concentrations, but superdosing removes that increase almost entirely, and in fact the concentration of IP3 is now lower than that of the negative control. So superdosing removes the excess of IP3 and prevents the buildup of IP4, something that works with this enzyme that clearly wasn't working with the previous enzyme, the Citrobacter brachii, when only used at 500 units. In fact, in this visual you can see quite clearly the dramatic effects between a regular dose of Quantum Blue and the superdosing effects. Although we've highlighted IP4 concentrations being reduced by 32% when you superdose, in fact the reduction in IP3 is even more dramatic. There's a 67% reduction in IP3 concentrations when you superdose compared to a regular dose of Quantum Blue phytase. So with respect to superdosing, in this particular section I've been focusing on IP4 and IP3. What I'd like to reinforce here is that IP4 and IP3 are made by normal phytase usage levels. They are not present in an animal which is not fed a phytase. They interfere with digestion and possibly as much as IP6. We really don't know at the moment, but we know they're anti-nutritive. The problem with IP4 and IP3 is they're very soluble in the stomach and they can move very easily into the small intestine where they precipitate, as I've mentioned, with zinc and interfere with protein digestion. In that regard, what we've got to think of when we think of superdosing is not just simply getting rid of IP6, but IP5, IP4 and IP3 as well, because all of these esters play a significant role in reducing the ability of the animal to digest its feed effectively. In that regard, superdosing needs to consider destruction of IP4 and 3 just as much as it does IP6.